You know, when we think about a bushfire, what we see are the flames, right? The smoke, the immediate, terrifying destruction. But what if I told you that long after the fire is out, a totally invisible threat is just lurking, waiting for the first rains to wash it into our most precious resource, our water? So what really happens after the fire? Let's get into it.
To really wrap your head around the scale of this problem, just think about the 2019-2020 Australian bushfire season. A staggering 6 million hectares burned. I mean, that is a truly enormous landscape, completely changed, and now it's covered in this residue that poses a huge risk to all the water catchments inside it.
You'd think rain after a fire would be the best thing in the world. And yeah, for putting out those last embers, it is. But here's the twist. That exact same rain is what kicks off the next crisis. It washes everything left behind on the forest floor straight into our rivers and reservoirs. So, what exactly is getting washed in?
Okay, so before we can even think about a solution, we have to identify the bad guys. What is all this stuff left behind by the fire, and which of it is really responsible for poisoning the water? It's time to unmask our sooty suspects.
So, under the microscope, here are our two main residues. On the one hand, you've got charcoal. See how it's kind of structured and porous, almost like a tiny black sponge. And on the other hand, you've got ash, which is just this fine, messy powder made of all sorts of tiny particles. They look really different, and as we're about to see, they act totally different in water.
And this table just lays it all out. You might look at that pure-looking charcoal and think, yep, that's the problem. But actually, it doesn't dissolve very easily. The real troublemaker? It's the ash. It's this messy mix of organic and mineral stuff, and the research is crystal clear. Ash is the primary pollutant that just wreaks havoc on water quality. So yeah, it's the ash we really need to worry about.
All right, so we've identified our main suspect, ash. But how does this fine powder actually pollute massive amounts of water? Well, it all comes down to one key scientific process. Let's dig in.
The process is called leaching. And honestly, the best way to picture it is like you're making a cup of tea. When it rains, the water flows over all that ash. And just like hot water pulls the flavor and color right out of a tea bag, that rainwater pulls all these soluble chemicals and organic materials out of the ash particles and carries them away.
But here's a really critical detail. Not all water is created equal when it comes to leaching. How effective this whole steeping process is depends massively on the water's pH, how acidic or alkaline it is. And this, it turns out, is a huge factor.
Just look at this chart. It shows how much gunk, in this case humic acid, gets pulled out of the ash at different pH levels. In more acidic water, less stuff leaches out. But in more alkaline water, which, surprise, is often what you get after a fire, the amount of pollution released just skyrockets. We're talking more than double.
And the end result of all this is a total disaster for our water quality. The pH and alkalinity can shoot so high they blow past safe drinking standards. The water gets super cloudy or turbid, full of all these suspended particles, and all sorts of harmful organic stuff gets dissolved right in, making the water unsafe and a real nightmare for treatment plants to handle.
Okay, so things are looking pretty bleak, right? The water is contaminated, it's a mess. But thankfully, science has an answer. Let's meet the cleanup crew and see if we can actually fix this problem.
So the key weapon in our arsenal is a process called coagulation. Sounds complicated, I know, but the idea is actually pretty simple. You add special chemicals to the water that basically act like tiny little magnets. They attract all those tiny bits of pollution, the dissolved stuff, the particles making it cloudy, and pull them all together into bigger, heavier clumps called flocks.
The researchers in this study used a specific four-step process. First, they add a polymer, which kind of starts grabbing onto the contaminants. Second, they add a coagulant, something like iron chloride, which neutralizes the electrical charges on all those tiny particles, helping them stick together. Third, you just stir the water gently, helping those clumps grow into bigger and bigger flocks. And finally, you just let gravity do the work. The heavy flocks sink to the bottom, leaving much clearer water on top.
So that's the theory, a neat four-step process. But here's the billion-dollar question. Does it actually work on this kind of uniquely nasty, fire-impacted water? Let's check out what the lab results say.
And the results are, well, they're pretty incredible. This dual coagulation process got an 84% reduction in turbidity, that's the cloudiness of the water, and it removed 68% of the dissolved organic carbon, which is all that nasty stuff that leached out of the ash. I mean, these are fantastic numbers.
This chart just shows you the difference in plain sight. You can see the super high cloudiness of the untreated water on the left, right? It's measuring about 24 units. Then look at the right. After the treatment, it's down to just 4. It's just a dramatic visual confirmation of how well this whole cleanup process works.
Now, it's not a complete silver bullet. The researchers were clear about one limitation. While this process is amazing for getting rid of particles and dissolved gunk, it doesn't really solve the problem of high alkalinity. That would need some extra treatment steps.
But the overall conclusion here is what's so incredibly hopeful. The study says, and I quote, "Fire-impacted waters can be effectively treated to remove soluble carbon by using commonly available coagulant materials." And that's the key part. Commonly available. This means we don't need some futuristic, super expensive tech. The tools to fight this problem are already out there in the water industry.
And that really leaves us with a critical question for the future, doesn't it? We know these fires are getting more frequent, more intense. This research shows we have effective tools to deal with the after effects on our water. So the real challenge now is, how do we get our water systems ready to use these solutions quickly and effectively when the next big fire inevitably strikes?